Hello and welcome back to California Geology. I am Dr. Robert Lopez, and today I want to talk about some of California's young volcanoes, in particular Mount Shasta up in Northern California. And if we look at my PowerPoint here, I'll cover Shasta and Lassen, and then I'll get into the Modoc Plateau and Medicine Lake volcano, and later on I'll finish off with Long Valley Caldera and some activity in Southern California. But first, if we look at Mount Shasta, it's considered a stratovolcano. Remember, these are the subduction zone volcanoes that occur along a convergent margin. If we look at the plate tectonic setting, we see that off of Northern California here, Oregon and Washington states, we have this Juan de Fuca plate, which is being subducted along this Cascadia trench under North America. Remember, the southern part of the Juan de Fuca plate is called the Gorda plate, and this is the Gorda Ridge. But we have a spreading ridge here where the Juan de Fuca plate and the Gorda segment is subducting under North America. If we look at the cross section down here, you can see there's seafloor spreading at the ridge, and then the trench, and then we see subduction and melting in the mantle wedge up above the subducting lithosphere. Recall that water leaking out of the subducting slab will lower the melting point of the peridotite mantle and cause magmas to form at these subduction zone settings. Now, Shasta, like all stratovolcanoes, is composed really of two phases, an explosive tephra phase and then the lava flow phase. Remember, tephra is the explosive ash that goes up, that's pyroclastic, and then the lava will flow out and pour out of the volcano. Here's a picture of the Mayon volcano in the Philippines, having the tephra or pyroclastic phase, and then this column collapsing. And remember, when the column of ash, volcanic ash, collapses, it forms these devastating pyroclastic ash flows that can travel over 100 kilometers per hour. Now, if we look at our table here, our table 5.2 in our book, on page 81, we see some recent eruptions. And what I'll look at here are the ones occurring here at the Shasta area. One thing they don't show on here is the most recent eruption of Shasta, which occurred in 1786. And that one was observed by a French explorer offshore of Northern California. Now, Shasta is really composed of four different cone building events that happened in the last 100,000 years. Some of the oldest rocks in the area, lava flows and domes, are about 600,000 years old. But the most recent eruptions, or at least what we see, occurred really in the last 100,000 years. And in this picture, we see three cones. We see the prominent peak of Shasta, which is called the Hotlam cone. Then there's Shastina, which is a satellite cone to the south of the main cone. And then you can see a third cone here called Misery Hill. So there's the Hotlam cone, Shastina cone, and Misery Hill. Now, the fourth one, we can't see. It's pretty eroded. It's not in this picture. It's called the Sergeant's Ridge cone. And here I have my Google. And on Google Earth, we can see here there's a Shastina cone, the Hotlam cone. You can see the Misery Hill here. And if we kind of look around the volcano here, in fact, there's this prominent peak here called the Thumb. Let's zoom in a little bit on the Thumb. And then there's a Red Banks Tuff here, which erupted about 9,500 years ago. But this little ridge right here, that's the Sergeant's Ridge cone there. Let's go back north here. And so again, we'll see the Sergeant's Ridge right in here, the Misery Hill, which are older. They're older than 15,000 years. They're considerably older. I'm not sure exactly of their ages. One way geologists can tell they're older is that these are glaciated. You can see this glacial valley coming down through here. Both the Sergeant's Ridge and Misery Hill cones have been bisected by glaciers, whereas Shastina and the Hotlam cone have not. So these have occurred in the last 10,000 years. Now, in terms of Shastina, this cone formed between about 9,700 years ago and about 9,300 years ago. And this cone building event, there's a dacite lava domes and some andesite flows. You can see some flows coming down here from this cone here. And then it did experience, perhaps through an earthquake or some sort of shaking, where part of the cone collapsed. You can see sort of this debris avalanche chute which takes it down here and spreads out over here. And in fact, the town of Mount Shasta is partly built on that debris chute. Another interesting young feature is this feature here called Black Butte. And Black Butte also formed about 9,500 years ago, similar in age to the Shastina cone. And it's very prominent because you see it right along I-5. You can't miss it. Now let's go back here and look at another thing that I want to point out here is that Shasta also has some prominent glaciers on it. And in fact, let's put the glaciers. We have some names. So the Whitney Glacier is probably the biggest one in California. In fact, let's zoom around here. And if we look here, you can see the sort of the ice. Here's the Whitney Glacier coming down. See the ice of this one here. And then there's also the Bolam Glacier here. See the ice? That's all glacial ice. And then another prominent one here is the Hotlam Glacier. A fourth one is this Wintun. Those are the biggest ones. The Wintun, the Hotlam, Bolam, and the Whitney glaciers. And notice they're mostly on the north or eastern side of the volcano. Right? Remember, south is over here, where Shastina cone is. Now, another thing about this Shasta cone, remember the Hotlam cone to be the highest peak, and up here we will have some steam, some fumarolic vents up at this summit cone. The eruptive history of Shasta. And if we look at this chart from the U.S. Geological Survey, we see that St. Helens in the Cascades is one of the most active of the Cascade volcanoes, erupting quite a bit in the last 4,000 years. But second on this list is Shasta. And Shasta has an eruptive cycle of about every 600 years, followed by maybe one of 200 years, 600, maybe a little bit less than 200 years. And then then there's another 600-year period going on here from about 1,000 to present, where there was an eruption about 200 years ago in 1786. And so if it's erupting every 600 years or maybe every 200 years, well, maybe Shasta it's certainly an active volcano, and it has high potential for an eruption, certainly in the next 100 years or so. But if it's following that 200-year cycle. But if it's following the 600-year cycle, then it's going to be a little bit longer time. Obviously, if it's going two eruptions, kind of closely spaced at 200 years, then a 600-year span, then a 200-year span, then a 600-year span to the 1786 eruption. So it's been over 200 years. So if we're doing every 200 years, then it's due for an eruption. Now, here's a picture of Shastina cone showing that debris avalanche chute there. And some of these andesitic lava flows from the Shasta volcano. I talked about Black Butte about 9,500 years ago. Here's that I-5 corridor there. And then one amazing thing about Mount Shasta is what we see today. Again, it formed really in the last 100,000 years. But there was truly a spectacular eruption that occurred here about 300,000 years ago. So if we look at your book here, there's a section that talks about it here, where literally the whole western 2/3 of this valley called the Shasta Valley is covered by this debris. And the picture in your book shows these rounded knobs. In fact, they're called hummocks. And if we look at that picture on our PowerPoint here, here we see Shasta, Black Butte, and we see these rounded knobs, which have really confused geologists for many years until Dwight Crandall, a geologist at the U.S. Geological Survey, came up with a startling analysis. And he said basically that an ancestral Shasta had erupted in a catastrophic eruption similar to the eruption of Mount St. Helens in 1980. So if we look at what happened in St. Helens, right, there was a massive eruption in 1980, and in that eruption, a big landslide triggered not only a eruption column, but also a lateral blast. And it literally removed about 2/3 of the volcano. And so here's a map showing the devastated area. And one of the deposits that's left behind are these landslide deposits, which are called hummocks. And hummocks are a series of conical hills, enclosed depressions, no true ridges, very chaotic displacement of rocks. And so that's what this is showing here, these little hummocks. And so that's what the analysis was here, that these are hummocks that came from this massive avalanche that occurred here about 300,000 years ago in the Shasta area. And it covers this Shasta Valley. So here's a map of Shasta, and it shows this whole area where this material came to rest. And so if we look at your book here, basically it describes it as a 45 cubic kilometers material spread out over an area covering 675 square kilometers. So a huge area. And then from those numbers, we can get the volume of eruption. Remember, St. Helens in 1980, that had about 1 cubic kilometer material erupted, 0.3 cubic miles, so about a kilometer. So this eruption here, 300,000 years ago at Shasta, is about 45 times larger. So truly massive eruptions. So what does that say in terms of oh, here are the hummocks for St. Helens. So what does that say about the future of Shasta? Well, volcanic hazards, right? For one thing, it's a potentially active area, volcanically active. It will erupt, maybe not in our time, maybe in our lifetime, but certainly it's going to erupt again. And then the other thing is, if this eruption, well, when this eruption happened, the volcano that must have been here must have been as massive or even larger than the present Shasta we see today. So anyhow, we'll stop here and we'll continue on as we go.